Okay, so in this video, we want to look at the Gram-Schmidt algorithm. And if you recall from our previous video, this is an algorithm that allows us to take a basis of a space of vectors V and to systematically transform this basis into an orthogonal basis of the vector space V. And the algorithm is remarkably simple, and all it uses is orthogonal projections. And again, the power of this algorithm is it allows you to transform any basis of a space of vectors to an orthogonal basis. So the original basis consists of the vectors v1, v2 up to vm. We will call the new basis vectors u1, u2 up to um. And again, an algorithm is simply a procedure, a sequence of a finite number of steps that gives a desired result. And here the desired result is transforming the basis B into one that is orthogonal. So here's the first step. Very simple. The first vector of our new basis u1 is simply the first vector of the basis B, v1. So we don't transform v1, we just take it to be our first new vector basis vector, sorry. So the question is now, what will be our second new basis vector? And this vector must be orthogonal to u1. Now just visualize what we have so far. Vector u1 is vector v1. That's our first basis vector of our new basis. So imagine this says vector v1, which is u1. And now we have vector v2. Now vector v2, because B is a basis, cannot be parallel to v1. So suppose that v2 looks something like this. Now imagine what we have right now. We're trying to look at what vectors v1 and v2 generate. Vector v1 is vector u1. And if you think of it, with vector v1, we already are generating this direction. But there is a component of v2 that is lying parallel to v1, right? Decompose vector v2 as a sum of two vectors. A vector that is parallel to v1 plus the orthogonal component. So you see vector v2 is simply this vector plus this vector, but if you think of it, you don't need this component of v2 because you already have v1 in your set to span to generate this dimension. So if you lose this vector, this part of v2, you lose nothing because you already have vector v1 to generate this dimension. So we can remove from v2 this vector. But if you think of it, what is this vector? It is the orthogonal projection of vector v2 onto vector u1. And the argument is that we can now take u2 as vector v2, but we only keep the component of v2 that is the orthogonal component to u1, because the component of v2 that is parallel to v1, we don't need this component because we already have u1 to span this direction. So we only keep this component. Well, of course, this vector plus this vector is v2, therefore the orthogonal component is going to be v2 minus the projection of v2 onto u1. And now with these two vectors, it leaves us with u1, which is this vector, and v2 minus its orthogonal projection onto u1 leaves you with this vector. And now you see that vectors u1 and u2 are perpendicular to each other. This is now vector u2, and this is vector u1. So these vectors are perpendicular to each other, and then we just have to keep going like this. How would you compute now the third new vector of your basis? Well, think of it. You will take vector v3, but v3 will have a component along u2, and v3 will also have a component along u1. But you don't need those two components because you already have u1 and u2 to span those directions. So remove from v3 its component along u1, but that is just a projection of v3 onto u1, and also remove the component of v3 along u2, and that is again the projection of vector v3 along vector u2. So by removing the components of v3 that are along u1 and u2, you can easily check with the same argument that the vector u3 will be perpendicular to u1 and u2. And you could check this algebraically if you want very easily. How would you verify that u3 and u1 are perpendicular? Well, vectors are orthogonal if they have a zero dot product. So dot u1 with u3, expand the whole thing out, you will get the zero vector. And how would you prove that u3 and u2 are perpendicular? Dot u3 with u2, expand everything out, and you will get the zero vector. But again, because we only remove from v3 a component along u1 and a component along u2, we don't lose anything through our space because we already have vectors u1 and u2 to span those directions. Let's do one more, and then we'll see how we can generalize very easily to the kth vector. How would you build the kth new basis vector? You will take the old basis vector v4, but now you already have u1, u2, and u3 to span 3 dimensions for you. So whatever components of v4 are along u1, u2, and u3, you don't need those components, so you remove them. So by removing them, you lose nothing because you already have those 3 vectors. And if you remove the components of v4 along u1, u2, and u3, you will be left with a vector orthogonal to all 3 vectors. So remove the projection of v4 onto u1. Remove the projection of v4 onto u2. And finally, remove the projection of v4 onto u3. And now we can generalize. How would we build the kth vector of our new basis? And this will be very easy to see, hopefully from what we have so far. So dot, dot, dot. And you see that to build any given vector in the new basis, you need to have found the previous vectors of the basis. So we'll have a recursive definition. The kth vector of our new basis, which will be an orthogonal basis, will be taking the old vector of the original basis vk, and now removing, and if you think of it, if you factor a negative sign from here, you'll have negative of this plus this plus this. So that's the negative of a sum. What are we summing? Well, we're summing projections. Projection of what? Well, it's v4, v4, v4. So it's always going to be vk. And we are removing the components of vk along the previous new basis vectors. So u1, u2, u3. And if you look at it, 3 is just k minus 1. 4 minus 1. So we remove the projection of the old vector, vk, onto the previous new basis vectors, say u I. And where does I begin and where does it end? Well, you have to remove every component of vk along the previous new basis vectors. So it starts, of course, with the first new basis vector, so I equals 1. And it ends, and here's where you have to be careful. It doesn't end with k, right? You see, if you have v4, there are only 3 previously found new basis vectors. So it doesn't stop at u4, but at u4 minus 1. So I goes up to k minus 1. Because before k, you only have k minus 1 new basis vectors. And this, of course, will be for k equaling 1, 2, all the way up to, of course, the mth, because we assume that we had m basis vectors. So we'll end with k equals m. And now we have the algorithm, which we can write much more concisely. All we need is this statement, and then this line, which tells you how you would compute. We start here with k equals 2. Up to m. And now with this line, u1 is v1, and this formula, we can compute u2, u3, up to um. And that is the Gram-Schmidt algorithm. And as we have discussed, the new vectors u1 through um will be an orthogonal basis of v. So that's our conclusion. So the first new vector of our basis is the original old vector v1. And to get the other vectors of our basis, u2, u3, and so on, we use this recursion. The kth vector, the new kth vector of our basis, which will be an orthogonal basis, will be the original kth vector of the original basis minus, and we are removing from all the previous k minus 1 new vectors the projection of vk onto the new orthogonal basis vectors. And this is again for k equals 2, 3, all the way up to m. And that is the Gram-Schmidt algorithm. And the conclusion, of course, once you do this, once you compute u2, as we have done here, compute u2, u3, u4 up to um, the new set of vectors u1 through um is an orthogonal basis. Of the original vector space V. And that's the Gram-Schmidt algorithm. Let's do one example of finding an orthogonal basis for a plane in R3 passing through the origin. But the algorithm works for any basis of any vector space. So here's the problem. So find an orthogonal basis of the plane pi in R3, say with the following equation. Let's go with x minus 2y minus 3z is equal to 0. And once again, we have a plane passing through the origin because the point 0, 0, 0 is a solution of the equation of the plane. Now, every time you want to find an orthogonal basis for a vector space, it's always a two-step process. First, find a basis, any basis, and then use Gram-Schmidt to transform the basis to an orthogonal basis. And every time you look for a basis of a space, you have to find the vectors or the points in the space explicitly. Well, here, this is describing the plane implicitly because we're told the points or vectors on this plane are the points x, y, z, where x, y, and z are the solutions of this equation. Well, whenever you want the basis, you have to find the points or the vectors in your space explicitly, so we have to solve the linear system. Again, I've picked a multiple of x to be 1 so that we already have a reduced echelon form of the matrix. So the points on the plane x, y, z, or again the vectors, same thing, points are vectors, vectors are points. Y and z are free variables, so let y be, say, s, z be t, and if you solve for x, you will get 2y plus 3z, therefore 2s plus 3t. As always, if you want from this to extract the basis of the plane, split up the two parameters, s and t. This will be s times the vector 2, 1, 0, plus t times 3, 0, 1. And if you look now, every point on the plane is a linear combination of the vector 2, 1, 0, 3, 0, 1, and so we have now a set of generators for the plane. So we have a potential basis given by V1 and V2. So the span of B is the entire plane because every point on the plane is a linear combination of the vectors V1 and V2, any multiple of V1 plus any multiple of V2. So that's the first condition of a basis. It must span the entire space, which it does. The only question left is we have to prove that the two vectors we have in what we hope is a basis are linearly independent. Well, we could fall back on the definition, but remember, two vectors are linearly dependent if one is a multiple of the other, if they're parallel. Therefore, two vectors are linearly independent if they are not multiples of each other. And this is really obvious. If V1 was a multiple of V2, well, what times 3 is 2? That's 2/3. Well, 2/3 times 0 is not 1, and 2/3 times 1 is not 0, so clearly V1 and V2 are not multiples of each other, therefore they are linearly independent. So B is indeed a basis of the plane pi. And as always, the dimension of the plane of any space is the number of elements in any basis of the space. We have a basis here with two vectors, so the dimension of the plane is 2. And again, intuitively this makes perfect sense. A plane is an infinite two-dimensional flat surface. Now that we have found a basis, the question was not just to find a basis, but find an orthogonal basis. Well, is this basis, v1, v2, orthogonal? Well, are the two vectors orthogonal to each other? Well, let's see. Vectors are perpendicular if they have a zero dot product. If you dot v1 with v2, you'll get 6 plus 0 plus 0, which is 6, which is not equal to 0. These two vectors are not perpendicular, so we have here a basis that is not orthogonal. Well, this is the part where we use the Gram-Schmidt algorithm to build an orthogonal basis of the plane. So let's just use Gram-Schmidt. Gram-Schmidt says the first new vector in your orthogonal basis, u1, will be simply the original vector of the original basis. So u1 is simply v1, and that is the vector 2, 1, 0. Let's compute now the new second vector of our basis, u2. Well, we take the second vector of the original basis, v2, but remember that v2 has a component along u1, and we don't need this component, so we subtract it. And the component of v2 along u1 is just the projection of v2 along u1. And this vector will be perpendicular to the vector u1. Let's compute this. So this is v2 minus, and recall the formula for the orthogonal projection. This will be v2 dotted with u1 divided by u1 dot u1 times the vector that we are projecting onto, therefore times the vector u1. Well, let's compute this and we'll have our new vector u2. The vector v2 is the vector 3, 0, 1, minus, let us now find these two dot products. So v2 dotted with u1, but u1 is just v1. So let's dot v2 with u1. We'll get 3 times 2, 6, plus 0 times 1 plus 0, plus 1 times 0 is 0, so we'll get simply 6. So v2 dotted with u1 is 6, divided by u1 dot u1. Well, here's u1, and if you dot u1 with u1, you'll get the sum of the entries squared, and you'll get 4 plus 1, 5, times the vector u1, which is 2, 1, 0. And now let's just compute this, and we'll have our second basis for the orthogonal basis, our second basis vector for our new orthogonal basis. Well, this is over 5, so let's factor the over 5. And you want here to have an over 5, so multiply by 5 over 5. Leave the 1 over 5 outside, and now find the three components. You'll have 5 times 3, 15, minus 6 times 2, 12. 15 minus 12 is positive 3. 5 times 0 is 0, minus 6 times 1, minus 6. 0 minus 6, negative 6. And finally, 5 times 1, 5, minus 6 times 0, minus 0, and you get 5. But now think of it. When you have a basis vector, all you need is a vector in the right direction. The length of the vector doesn't matter. So if I say to you, you have a vector in the basis, u2, well, 2 times u2 would give the same direction. 3 times u2 would give the same direction. Pi times u2 would give the same direction. So any vector that is in the same direction as u2 will do the job. And the idea here is, it's better to have a vector with integer entries because it will make the calculations simpler. So instead of taking u2, and this is where we slightly deviate from the algorithm, but we do so for a good reason, so as to avoid fractions. So we can drop the 1 over 5, or think of it as replacing u2 by 5u2. This will span the same direction, and we'll take the vector u2 to be 3, negative 6, 5. And let's see if we have what we wanted. We were hoping for an orthogonal basis of the plane. Therefore, these two vectors should be orthogonal to each other? Well, let's dot them. 2 times 3 is 6, plus negative 6 is 0, plus 0 is 0. So indeed, u1 and u2 are perpendicular. So we now have our orthogonal basis. And I'll write b subscript on to say this is now a, OG, for saying that we have transformed b into an orthogonal basis, and the new vectors are u1, u2, and if you want them explicitly, well, vector u1 is 2, 1, 0, vector u2, after we remove the 1 over 5, is 3, negative 6, 5. And we now have an orthogonal basis of this plane. One thing to check also, we have checked that both vectors are perpendicular because their dot product is 0. But if you recall, these are supposed to be vectors on the plane or points on the plane, so they should be solutions to the equation of the plane. Let's verify this to just make sure that we get two vectors on the plane, not just orthogonal to each other. So 2, 1, 0 should be a solution of the plane. 2 minus 2 times 1 is minus 2 is 0. Minus 0 is 0. Check. The other vector should be 3, negative 6, 5. Let's plug it in. So 3, negative 2 times negative 6 is plus 12. 3 plus 12 is 15. Minus 3 times 5 minus 15, and that is equal to 0. So the vector or point 3, negative 6 is a solution of the equation of the plane. Therefore, it is a vector slash point lying on the plane. And let's do one last little application. Now that we have an orthogonal basis, let's take a point on the plane and ask to express it as a linear combination of our two new basis vectors. And the fact that we have an orthogonal basis will allow us to solve for the linear combination, if you recall, not using or solving a linear system, but instead using the dot product. Let's take any point on this plane, and that would be a solution to the equation. Well, we have found all of them, so we could take any s and t, and we will have here a point on this plane. Take, say, s equals 1, t equals 1, then you'll get 2 plus 3, 5, 1, 1. And let's verify that the point 5, 1, 1 is a point on this plane. 5 minus 2 times 1 is 5 minus 2, 3. Minus 3 times 1, minus 3. 3 minus 3 is 0. So the point 5, 1, 1 is a point on this plane. And now we'll ask to express the vector 5, 1, 1 as a linear combination of our two orthogonal basis vectors. So we'll say, how can we get 5, 1, 1 with a multiple of u1 plus a multiple of u2? Because this should be possible, as any given vector on the plane should be a linear combination of the two orthogonal basis vectors. And if you remember, at this point, if the basis was not orthogonal, you would have to solve the corresponding linear system. But because we have an orthogonal basis, we can do better. We know that C1 is this vector dotted with u1 over u1 dotted with itself. So let's do that. So if you call this vector u, C1 is u dotted with u1. So 5 times 2, 10, plus 1 times 1, 1, 11, plus 0. So we get 11 over u1 dot u1. So if you dot u1 with u1, you get 4 plus 1, 5. So you get 11 over 5 times u1, which is 2, 1, 0. Now plus C2 times U2. Well, here's U2, 3, negative 6, 5. But if you recall, to find C2, it will be U dotted with U2 over U2 dot U2, right? If you recall the result, the ith coefficient was just a vector dotted with the ith basis vector divided by the ith basis vector dotted with itself. So Ui dotted with Ui. This was our conclusion in the previous video looking at an orthogonal basis. Let's find C2. It will be U dotted with V2, U2. So 5 times 3, 15, minus 6, 9, plus 5, 14, over U2 dotted with U2. So 3 times 3 gives you 9, plus 6 squared gives you 36, plus 5 squared gives you 25. If you add those two up, you get 50 plus 11, 61, plus 9, 70. And you have your linear combination. The point on the plane, or the vector 5, 1, 1, is 11 over 5 u1 plus 14 over 70 u2. Well, we can simplify a bit, because 14 over 70 well, we can cancel a factor of 7, right? 14 is 7 times 2. 70 is 7 times 10, so we're left with 2 over 10. We can also cancel a 2, and we're left with 1 over 5. So we'll get 11 over 5 u1 2, 1, 0 plus 1 over 5 u2 3, negative 6, 5. And just for good measure, let's verify that this will indeed give us vector u. But the idea is, because we had an orthogonal basis, we were able to find the coefficients of the linear combination expressing the vector u without solving a linear system, just with the help of the shortcut formula with the dot product giving us the coefficients. Let's check. This is all over 5, so this is great. We'll have 2 times 11, 22, plus 325 over 5 is 5. Check. We'll have 11 minus 6, well, that's positive 5 over 5 is 1, check. And 11 times 0 is 0, plus 5 over 5 is 1, check. And that is why having an orthogonal basis is so nice. Whenever you want to express any vector in your space as a linear combination of the new orthogonal basis vectors, you don't have to solve a linear system. You can just use the dot product to solve for the coefficients one at a time. And that is much more efficient.